Good morning. My name is BOUJNOUNI, and today I'm going to talk to you about the heart rate variability prediction based on the combination of wavelet decomposition and LSTM neural networks. Cardiovascular disease are the number one cause of death globally. More people die annually from CVD than from any other cause. And heart failure has become a frequent manifestation of CVD, affecting a lot of people worldwide, and which means that the heart is unable to pump blood around the body properly. Recently, most of studies reported in the literature focus on the utilization of heart rate variability as a predictive factor in patients with heart failure. And a heart rate variability presents the time interval between two consecutive QRS complexes lying adjacent in ECG. So here we propose an approach based on the combination of wavelet decomposition and LSTM model. So instead of testing LSTM model directly with the actual heart rate, we take the sum of all wavelet coefficients of each level obtained from wavelet decomposition to test the LSTM model, and then compare the results of the both methods. In the wavelet decomposition, filters of different cutoff frequencies are used to analyze the signal at different scales. So the process consists of a number of successive filtering steps in which the time series is decomposed into approximation CA, which represents the low frequencies, and several details components, CD1, CD2, etc., which represents the high frequencies. Long-chain memory are a special kind of RNN recurrent neural network capable of learning long-term dependencies. So a simple LSTM cell consists of 4 gates. The 4-gate gate F decides which information should be thrown away or kept. Input gate is used to update the cell state, and we have the cell state gate. At this step we have enough information to calculate the next cell state. And we have the output gate. This decides what's the next hidden state should be. BLSTM, bidirectional long-chain memory, is an extension of the unidirectional LSTM, which is designed to capture the past and the future information of sequential data, and it has 2 parallel layers, propagating in 2 directions, the forward and the backward path. So this structure can improve LSTM model performance and forecasting process. So here we apply the proposed approach using the heart rate time series obtained from the database MIT PH, and we use LSTM neural network with line in Windows 16. So the main hyperparameter of the model is summarized in this table. We implemented the prediction using Keras library in Google Colaboratory, and then we test the performance by predicting the value of testing data and comparing with actual data. So what did we do here? So firstly, we train and test the model directly with the sequence data, and in the output we have the orange line represents the actual data and the blue one represents the predicted data, and the model has mean squared error of 6.7. Secondly, we decompose the time series using with the decomposition. We applied the species date. We obtained 1 approximation and 7 details coefficients, and then we summed them up to obtain the forecasted data, and we obtained a mean squared error of 1.32. So here we compare the 2 figures. You can clearly see that our approach, which the combination of LSTM with wavelet decomposition, has been able to capture the overall trend, and it gives the lower mean squared error of 1.32. We can conclude that the wavelet decomposition influence on forecasting performance in the LSTM model by giving a high performance and better results. In future work, we plan to focus more on the effect of various parameters such as the choice of wavelet functions, the level decomposition, the choice of sequence window size, the number of hidden layers, the number of train epochs. Thank you.